Welcome and thanks everyone for joining us today. We have a wonderful presentation for you on creating safe electrical test areas. A little information about Seaward. We have a dedicated customer support team which can provide phone or video conferencing for product demonstrations and support. We have a wealth of knowledge forged through close interactions with our customers to deliver innovative products which improve the testing process, including traceability and efficiency. Our unrivaled range of test equipment are used in production lines, PV installations, medical facilities, construction sites, and tool cribs. Seaward's head office is located in Peterlee County, Durham, and has a sister location in Tampa, Florida. I'm Brad Perryman. I'm the Senior Sales Engineer here in Tampa, Florida, and I've been with Seaward for over 6 years. Our presenter today is Nathan Barwell. He is the C&P Category Manager. Nathan has been with Seaward for over 10 years and is based in the head office located in County Durham in the northeast of England. I will now hand over this to Nathan.
Thanks, Brad, and a warm welcome to everyone joining us today. Thank you very much for taking time out of your day to come and hear us talk. Today we're going to be discussing how to create a safe working environment in electrical test areas. We're particularly focusing in on those of you that are working in production line type environments and want to make a nice, safe environment for your operators to do their end of production line safety testing. So let's have a look at what we're going to be discussing today. Firstly, we'll be discussing the effects of shock and how to understand exactly what happens when the body does receive an electric shock. From there, we'll talk about how to protect yourselves against that shock, and ultimately, which will lead us on to creating the safe environment. We'll also discuss the type of test stations you might want to employ within your organization. From there, we'll start to discuss operator training, the kind of training you should be giving to your operators, and the skills that they do require in order to keep themselves nice and safe when performing electrical safety testing. Finally, we'll discuss the actual test equipment itself and how that can help you to aid you in creating a safe working environment. So if we think about electric shock, there are a number of factors that could increase the severity of the shock. The first thing is the kind of level of voltage and ultimately the level of current that bypasses through the body, the condition of the body at the time we receive the shock, the path the current takes through the body, and finally the duration of the exposure. All of these factors could significantly increase the risk of shock and the risk of severe shock to an operator, but we'll discuss them individually as we move through the presentation. So firstly, let's talk about the levels of shock and the kind of effects that an electric shock can have on a person. We've all seen the kind of comedic guy touches the wire and starts shaking. And whilst that's effectively true, there are a number of kind of injuries that can occur through electric shock. Those being an electric shock itself. From there, we can receive burns. So where the current exits the body, it can produce burns. One of the kind of hidden dangers of receiving an electric shock is the involuntary movement that occurs potentially when we receive the shock. So if we take a good example of a guy working at height, he may be up a ladder, he touches a live conductor, receives a shock, and through an involuntary movement, he falls off the ladder and injures himself through falling. Again, the main cause of that was the electric shock, but that may be kind of hidden in the fact that it gets recorded as a fall. And then finally, sadly, the electrocution, which ultimately proves fatal. So we do need to kind of take electricity seriously, and ultimately it's one of these things that you can't see, but it doesn't mean that the danger isn't present. Now let's have a look at the reality of current exposure. As an example up on the screen now, you'll see different physiological effects on both men and women who react slightly different to current exposure. And for this example, we've looked at it at both DC and 60 Hertz AC. Now, in the majority of production line environments, you're probably going to be testing at AC. So let's have a quick look at some of the levels where that affects the body. So at about 0.4 for men, we may start to feel a slight sensation. That sensation isn't always directly comparable to an electric shock. There are many ways that can kind of manifest itself. For those of you that have kind of ever felt this, sometimes on a metallic surface where there is current flow, if you were to run your fingers over the top of it, it can feel almost greasy. And that greasy feeling is the actual current itself, and the sensation that you're receiving. At around kind of 1 milliamp-ish, that's really our kind of threshold of perception. This is where you'll really kind of feel that there's something occurring. It can feel slightly like pins and needles. At around 5 up to around kind of 9 milliamps for men, this is where our kind of pain threshold starts to come in. You will feel it. It will feel painful. You still have kind of voluntary muscle control, so you still can react, and if you were to contact something, you still have the capability of pulling your muscles away. This is what we call our maximum kind of let go threshold. Slightly higher than that, so above 10 to maybe 15, 16 milliamps. Again, it's now the pain is increasing, but now we can start to have these involuntary muscle controls. So, your arm may fling backwards, you could fall off of things just because your body reacts in a way that you weren't expecting. Where it starts to become really kind of problematic and I guess a threat to life is up around kind of 15 plus to kind of 20, 25 to 30 milliamps. At that level, we're really at severe pain now. So we're going to be in a lot of pain. We really will struggle breathing. Our muscles may be contracting very, very hard. So it's difficult for us to kind of expand our lungs in order to breathe. And we've pretty much lost all control of our muscles. So at around this level, this is really where, if we were to be receiving an electric shock, we really would require some external support in order to get us away from that level of danger. So this is where things like automatic disconnection, or even if any of you have ever seen the big hooks that can pull people away from the current, we may need some sort of external support. Unfortunately, up at around 100 milliamps, if we're exposed to that level of current for kind of 3 seconds or longer, it will start to kind of interfere with the rhythm of the heart. So we really will be at that point into kind of heart attack territory. And this is potentially where it starts to become kind of a fatal response to an electric current. So we mentioned briefly before that the condition of the body can play a factor in terms of the severity of the shock. Now, as a kind of average, the human body has a resistance of approximately 1 to 2 kiloohms. It's true that most of that resistance to current is pertained through our skin. So the skin provides that majority of resistance to current. Once the voltage penetrates through the skin and the current starts to flow kind of inside the body, if you like, we're now into kind of our nervous system. So therefore, as you know, our nerves are there purposely designed to carry current. That current is electrical signals from our brain, which allows us to move our limbs. Once current penetrates and into the nervous system, then it can flow much, much freely throughout our body, and is therefore much, much more of a problem for you and I if we were to receive that kind of shock. That's why if any of you are involved in the medical testing kind of environment, when we do tests for electrical safety in that arena, we're looking for much, much lower currents, because those lower currents can be much, much more problematic than the kind of currents that you and I would be capable of withstanding with an intact body. But the skin itself is porous, so we do need to take into account that the skin has small holes. They can open up. So things like sweaty environments, if you're hot, if you're testing in a humid area, your skin's likely to be more or less resistant, I should say, because your pores will be open and therefore current can flow and puncture much easily. Now, once that current is inside the body, we need to consider where it's going to flow in order to cause us a problem. Firstly, it's true to say that we will only receive a shock where current enters our body at one point and exits it another. It needs that path through our body and out to ground. If that doesn't exist, then we won't receive a severe shock. Now, the biggest problem for us as humans, as we saw in the earlier table, is that potentially it affects our rhythm of our heart. So any kind of path where the current flows across the chest is going to be most problematic for you and I. Now, as you can see in the kind of picture on screen, one of the worst cases is where it flows into a hand, across the chest, and out through the feet to ground. Why is that such a problem? Well, our feet are generally always in contact with ground, so we're effectively grounding ourselves when we're stood anywhere. So if we were to receive an electric shock and current was to flow through our body and away to ground through the feet, then that's going to really pose a problem to us as humans. It's also true that current path could flow across the chest from hand to hand. So it may be that we're working on a product, we're in contact with a live conductor with one hand, and potentially we may be resting the other hand on the chassis, and that chassis of the product is grounded and flows away to earth. Again, by doing that, if we were to come into contact with live current, that will flow through the body onto the chassis of the product through our other hand and away to ground via the product's ground path. Again, that could really take it across the chest and be problematic for us. So we need to consider these factors when we're thinking about designing a safe working area. And really there's three things we can do to protect ourselves against shock in an electrical test environment. The firstly is we look to just simply reduce the potential for current flow through the body. So in order to do that, we simply look to eradicate any current paths. So can we take away any potential ground path through the operator? We'll discuss ways of doing that as we move through the presentation. Secondly, we can look to reduce the duration of the exposure. So have we got methods of disconnecting the fault currents in the event that something was to go wrong? Now those devices could be manual disconnects, so things like emergency stops, but they could also be automatic methods of disconnection. And ultimately, we can look to reduce the risk of occurrence happening at all. And we can do this by training the operators to understand the hazards involved in their job, to be able to spot those sort of problems that could cause an electric shock. And hopefully through good training, we can eliminate the risk. So let's talk about actually creating a safe working environment. We often get asked, well, what should we follow? What kind of guidance is there available on the market for us to follow and ensure that we're creating a safe working environment? Well, for those of you operating kind of a European territory, we do have European standard 50191 that will help us to create a safe working environment. For those of you in America, we have our OSHA requirements. Again, they will help us, and we'll just discuss some of those briefly now. So for EN 50191, again, it's specifically designed to aid those who need to create a safe working environment when hazardous voltages are potentially being worked on. They make a number of statements that govern when we should look to employ the guidance within EN 50191. And I'm going to talk to you about one specific one here now. And you'll see it's the middle one. Voltages at frequencies up to 500 Hertz, exceeding 25 volts AC or 60 volts DC, if the resulting current through a non-inductive resistance of 2000 ohms exceeds 3 milliamps AC or 12 milliamps DC. So how does that relate back to what we do in terms of a production line test? Well, firstly, those of you that are involved in that will pretty soon realize that most of the tests we do, particularly when we're talking about the high pot dielectric withstand tests, is that they're typically kind of 1000 volts or greater. Generally, they are kind of at AC, 50, 60 Hertz, or we do DC ones, which again are at much higher current, much higher voltage levels. So we know that we're ticking the box in terms of the voltages. Could the resulting current flow through a non-inductive resistance of 2000 ohms? Essentially what that's saying is, could that current flow through a human being? Typically, if we have an operator there, then the chance is yes, we could be exposing our operators to that level of voltage. And ultimately, could that current exceed either 3 milliamps AC or 12 milliamps DC? Now, again, it's true to say that a lot of production line testers are capable of currents far exceeding 3 milliamps AC. Some go up as high as kind of 100, 200 milliamps AC, sorry. So if you have that level of tester, then you need to consider the safety aspects of it. There's also the point of what's deemed a safe and good test. And in many standards for manufacturing of equipment, so if we take, for example, the lighting standard actually calls for a minimum or a maximum pass limit of 5 milliamps when performing a 1500 volt AC hypot test. So we already know that between that level of safety and the level of pass or fail for that particular product, we've got a 2 milliamp window. So we should all automatically be thinking that we definitely need to be performing this test because our voltage is at 1500 volts and our pass limit is 5 milliamps. So we can take into account the level of test, but we should also look for the level of current the tester is capable of. And under fault conditions, could that tester potentially, if someone changed the test sequence, deliver the full amount of current that is potentially available to it? And if that answer is yes, then we really should be looking to create a safe working environment. Now, OSHA 29 CFR Part 1910-332 talks about, again, the limits for kind of safe working. And in this case, it's where exposed voltages are in excess of 50 volts. So again, we definitely know that for most hypot tests, we're going to be well in excess of 50 volts. And subpart S particular talks about the training required in order to make your operators qualified to perform such testing. So there is plenty of guidance out there. We will link to the relevant websites a little bit later on in the presentation. So before you start creating a safe working environment, we kind of need to look at these guidance documents to help us comply with the requirements within. But ultimately, what are we looking for? Well, there's four main areas that we really should focus on. The first one being, do we have insulated test areas? The second one being, do we have a safe method of disconnecting the supply in the event that something does go wrong? Have we set up things like prohibition zones and safe distances? And do we have sufficient warnings or information to alert people to the function of the actual area itself? Now, these things can be broken down into two clear kind of parts, really. The first one, insulated test areas, safe disconnection of supply, is all about protecting the operator, the person in the test area actually performing the tests. The second few, well, they're all about kind of keeping non-trained personnel safe. So this is keeping people maybe well away from the area, allowing them to see quite clearly what the area's use is, and therefore that they can understand that it's not an area that they should be in. So if we start to break these things down into kind of single elements, we can start to talk about the kind of pieces of the jigsaw puzzle that will ultimately come together to create a safe working environment. And the first thing to consider is the test bench itself that you're going to use. Now, ideally, you would want a fully insulated test bench. You can see in the example on the picture that the test bench itself is all made of wood. Wood is non-conductive, so that would be absolutely ideal. It may not be possible to have a wooden bench. It may be that you're already working with a certain environment and you may have to use things like metal frame benches, in which case we should certainly consider insulating the top of the bench, the area in which the product and the test equipment will sit when we're performing the test. Now, just as good practice, if you are going to fit any kind of insulated topping to your desk, we would certainly recommend not fixing it down with conductive fixings. Again, particularly if you have a metallic bench, you don't want to accidentally create a point where, in the event that stray current flows, it could come into contact with a screw that you've punctured through the insulated top, which is now into contact with the metal. So you could inadvertently create a path where current is flowing onto the legs of the bench, for example. Your operator touched them without knowing, and potentially puts himself in danger territory. Another kind of good practice when we are creating a safe working environment and training the operators is to really understand that during the time you're performing the test, that it should just be the item under test and the test equipment and any kind of leads and probes that you may need to use at the time. What we shouldn't be doing is having loads of tools or spare parts lying around that, again, could invariably create a path to ground. So the operator comes along, decides he needs a particular tool, he goes and picks that up, and fortuitously that's just in contact with a live part. Again, he could be putting himself at risk. So always make sure it's just the item and the test equipment needed at the point of doing the test. And then again, to ensure that nobody can kind of come into contact with it, always ensure that your test bench itself doesn't extend outside of the test area that you've designated for safety. Once we've created a bench, or if we need to create an insulated top, we should then look at things like insulated matting. Now again, insulated matting could be used on top of a bench, but more commonly it's involved in putting on the floor to create that barrier between the operator and the ground. So you should always look to install this, particularly if you have metal, concrete, or any kind of ceramic flooring. And again, as I discussed, it can also be used to cover worktops. Well, the next question is always, well, what kind of rubber matting should we be looking to use? Well, there is an international standard for rubber matting, which is IEC 61111. And you'll see on the table here, this table is taken from IEC 61111. And you'll notice that there are different classes of rubber matting. And those different classes relate directly to the voltage withstand potential of the rubber matting. You'll notice there is a 7,500 volt and 11,000 volt 250 for class 1 rubber matting. That would be kind of the minimum that we would recommend for anyone using any of the Clare testers or the Seaward testers. You will know that they have generally a maximum voltage output of 5,000 volts AC and 6,000 volts DC. So we want to make sure we're at least capable of withstanding the maximum output of the test equipment. In terms of the sizing of the rubber matting that you do choose to use, there's no maximum size, but it should be sufficient to cover the working area. Certainly if the operator has to move around, consider all of the points at which he may need to stand and ensure that rubber matting is covering that area. There is a size in terms of how small it should be. It should be no smaller than 600 millimeter by 600 millimeter. Again, that just gives enough room for the operator to kind of shuffle from side to side without coming off of the rubber matting when performing the safety testing. This is probably one of the most important kind of elements of creating a safe working environment, particularly for protecting your operators. So we would generally always recommend installing rubber matting into any electrical safe test area. We can then look at the kind of external protection, so how we keep people away from the test area. And we do that by creating exclusion zones. Now, exclusion zones can be very, very simple. They can be a simple post and chain link to specific kind of test cages. But essentially, the idea of an exclusion zone is to prevent access to the test area by anyone that's not trained to be in there. These barriers should be sufficiently far away from the product under test so that the person cannot effectively reach in and touch the product during the test. So it's all very well our test operator's nice and safe, he's stood on rubber matting, but someone walking behind the test area, he's probably generally going to be on regular concrete flooring. What we don't want to be able to do is for him to be able to reach across and touch the product under test. Now, in EN 50191, the distance away from the product will vary dependent on the height of the barrier that you do choose to use. So if it's a waist height, then a human could reach a lot further than, say, if the barrier was up at kind of around shoulder height. So that there are set distances in EN 50191 that will help you to determine how big your test area needs to be. Now, one thing to consider is if you are creating a prohibition zone, always make sure that whatever you do choose to use to block off the kind of walkways or work areas from the test area, make sure that it retains good visibility into the test area. Again, if the worst was to happen to the operator, we want to make sure that someone always has an eye on him at all times, so that he's not potentially left to continue receiving an electric shock if the absolute worst was to happen. So we certainly wouldn't kind of advocate creating a totally enclosed room where only the test operator goes into to perform the test. If you do that kind of setup, certainly make sure you have windows where it's possible to see. Now we'll talk about kind of the kind of warnings we can put out to the world, and information that we can give to ensure people understand exactly what's going on. And the first one is to consider installing kind of signal lighting. Now, signal lighting shouldn't be confused with test status. So this sort of lighting isn't a green for pass and a red for fail. This is more green for safe, red for unsafe. Traditionally, the way this works is if the test equipment is switched on, then the item would be in its green state. The equipment is switched on, it's potentially ready for operation. Once the test is started, then essentially the beacon should flick itself up to red, and that alerts everyone to the fact that the area is now live and certainly shouldn't be interfered with during the point at which the light is on red. For those of you that do have kind of the Seaward testers, we always install a point at which you could plug an off-the-shelf beacon into the tester, and that takes a signal directly from the high voltage output. So as soon as the voltage hits unsafe levels, i.e. kind of 25 volts AC, 60 volts DC, the tester will switch the voltage up to red, or switch the beacon, sorry, up to red to alert everyone that potentially unsafe voltage is present. Finally, let's discuss the electrical supply for the test area itself. We should certainly include methods of disconnecting the voltage from the entire area in the event that something was to go wrong. And there's two things we can look to install to do that. The first one being what we call emergency stops. You'll see them in the image on screen. So they're generally a big red button with either an orange or a yellow background. So there's a good high contrast between maybe the walls. So they're easy to spot, easy to find in the event that someone needs to hit the off switch. What these are designed to do is effectively take the main supply out to the area. Now, from a common sense point of view, we would always advocate installing both one inside the area and one outside of the test area. Effectively, if the operator spots something wrong and needs to cut the power in an emergency, he has the ability to just hit the button and take the supply to the test area out. But similarly, if the worst thing was to happen and the operator was receiving a shock, we want to be able to isolate the area before we put anyone else in harm's way and have them enter the test area. So always make sure there's one outside of the area, so if needs be, that can be disconnected prior to anyone entering the test area. The other kind of automatic element that we really should consider putting in is an RCD or GFCI device, so something that monitors the difference in the current flowing in the live and neutral conductors. And if there was to detect an imbalance, then it will automatically cut the supply to the area. So we would always make sure putting both of these features in tandem, so you have a manual disconnection method, but you're also backed up with an automatic method. And finally, just a bit of information on kind of warning signs. So again, we have trained personnel. We maybe have the guys doing the testing that understand exactly what the area is for. We may even have trained our warehouse staff or other production staff who are kind of in and around the test area, so they know exactly what's going on in there. They know they can't go in during a red light scenario. But we may have visitors, we may have other kind of contract staff working in there. So we should always make sure that the area itself is significantly signed so people know exactly what's going on there, and ultimately they know it's not an area that they should be entering. So you'll see kind of a couple of examples: danger, high voltage test area, do not enter when red light is on. All of these kind of signs will make it very clear to anyone that maybe hasn't had training that that area is just simply off limits to them. I just wanted to, at this point, just make a special note about ESD type areas. we commonly asked about creating a safe working environment, and oh, I don't need to comply with this because I have an ESD area. And it's commonly mistaken that ESD is all about safety. Well, that's not necessarily so true. It's generally there to protect the equipment from a static discharge. And by doing that, what effectively we're doing with any kind of ESD, whether it's flooring, whether it's tabletop matting, whether it's clothing, foot straps, we're effectively creating a path to ground. So you can already see from what I spoke about before, we don't want a path to ground. ESD is all there to create that path to ground. So our advice is never create a safe working environment in an ESD type environment. If you do have to do it, then consider again all of the factors we spoke about. So bringing in things like isolation matting, so that the area itself, it may be an ESD floor, but we make sure it's covered with rubber matting. It will create that ground path that we don't want. So our advice is just, if you are creating a safe working environment, never do so in kind of an ESD type area. So at this point, we're just going to take a break from the presentation to kind of get you guys involved a little bit here. So we're going to ask, which of the kind of previous features that we've spoke about are you currently employing within your test area? So I'm just going to bring a quick poll up. We'll give you a minute or so to answer them, and then we'll have a look at your responses.
Thank you, everyone, for your input in the poll. Appears that we got a good spread there between all the different options, and rubber matting and warning signs were used the most. Again, thank you for your participation.
So now we've created all the individual elements that ultimately sum up a safe working environment. Let's have a look at some of the ways you can create a test station. Traditionally, there are four kind of main ways of setting up a test station. So there's a test station without automatic protection against direct contact. What that means is effectively the operator can touch the product under test. We have test stations with automatic protection against direct contact. Therefore, there's a barrier between the operator performing the test and the actual product under test. We can also talk about temporary test stations and laboratory or experimental stations. Both of those really come into play in certain environments where it may not be practical to set up one of these type environments, or we may have large products that we need to move the test area to the product rather than the other way around. But we're going to traditionally focus on the first two, the test station with and without automatic protection, because both of those play a factor in how you would set up an area for temporary test stations or indeed kind of laboratory type environments. So let's first start talking about a test station with automatic protection. So as I said previously, a test station with automatic protection against direct contact simply stops anyone from coming into contact with the item under test during the time that the test is being performed. Now, traditionally, this is performed by dropping the item into an enclosure, as you can see on screen. We open a lid, we put the product inside, we make all of the relevant test connections in order to perform the test. We close the lid, we start the test away, and anything that could go wrong is going to happen inside a nice insulated box, keeping us nice and safe from harm. This is probably the ultimate safe way of performing testing. It may not always be the most practical because of the size of enclosures, and therefore things like the weight of doors and other kind of health and safety risks that could pose. But it probably would be deemed as being the safest way to perform testing. Most often, the test enclosure itself will be fitted with some sort of interlock system, so that in the event that the door was open during testing, the power to the equipment under test is instantly kind of removed. Commonly, that is done in tandem with the test equipment, and we'll talk about interlock features on test equipment a little bit later. The other main advantage for creating a test area with automatic protection, i.e. inside an enclosure, is that we can drastically reduce or remove altogether any kind of prohibition zones that exist around the test area. They can certainly become much, much smaller because the risk of an outsider receiving an electric shock becomes exactly the same as the risk of the operator, which is effectively none. The product is being tested safely away inside a box. So therefore, the consideration in terms of how much space do we have to give, how much reach space do we have to move between the point of test and the workways can be much, much smaller, because the simple fact is we physically cannot come into contact with the product under test. So let's have a look at that on a kind of production line environment. Here you'll see a kind of ideal scenario for an item with a test enclosure. So let's point out the individual elements. We have here the test enclosure itself, in which the product is being tested. We have the test equipment. We have a beacon which would display when the area is live or unlocked or disconnected. You can see the benches constructed from insulating material, so that effectively if there was a problem, and if you do use any kind of aluminium chassis for your frame, again, it's still insulated via the bench. There'll be rubber matting on the floor, again, just as a secondary level of protection for the operator. But you can see there's no real kind of prohibition zone other than the small area in which the test operator's working. We still have things like signage to alert people to what the area is, but there's no real kind of barrier between the guys and the area of test. So it can be very, very effective to test in this method. But again, if you are manufacturing different size products that maybe require different size jigs, it's not always the most practical of methods to ascertain. So the other way you could look to set up an area, and it's probably more common, is a test station without automatic protection against direct contact. Effectively, there's nothing stopping the operator from touching the item under test. Again, from a practical point of view, it may be that this is the only method you have to set up. Talking about temporary test stations, you may have to go to the equipment itself in order to perform the test. So you may have to take the individual elements with you in order to create a safe working environment. So we know we can come into contact with it, and therefore we have to take extra consideration to ensure that the area in which we're going to be doing the testing is fully isolated. The other thing to think about is, in many instances, the operator may have to use physical test probes in order to make the test connections. So that may not be possible to do inside an enclosure anyway. And if that is the case and we are using probes, we need to consider training the operator to be able to use those probes kind of effectively and ultimately safely. Back to where we spoke about, in this kind of environment, the operator can come in contact with the product, never ever have them testing in an enclosed room where there's no visibility. Let's have a look at a real world kind of scenario for this type of environment. So here we can see a kind of test station with automatic protection, without automatic protection. You can see here the E is the operator, the skilled person doing the testing. You can see all of the individual elements that we spoke about earlier on. So we have the test equipment, we have some beacons alerting everyone to the area. We have some emergency stops both inside and outside of the area, along with warning signs alerting people to the function of the area. And you'll see in this case the production line is an open production line. The test area is very much part of that line. So we have to consider both the area around the operator and the area in which people could be working or walking. So in this case, we've created a full kind of squared off situation, which is well away from the item under test. So the dispatch clerk and the guy wandering around the factory physically cannot come into contact with the product. They can't reach over. The barriers are a sufficient distance to enable that separation to exist. One note for those of you in America, the NFPA, the National Fire Prevention Association, recommend a distance of 3 meters between any kind of unskilled workers and any energized conductors. So for reference, you can look up NFPA 70E, and that's table 130.2. So effectively, we would need to ensure that our barrier system is 3 meters away from, in this case, the washing machine under test. So hopefully that's given you a good idea of the way you could look to set up a working environment. It's very much dependent on the current methodology that you have for your production, whether an enclosure would fit, whether it's possible to fit that into the enclosure under test, or whether you need to consider the kind of environment without automatic protection, in which case the shift in terms of focus for protection becomes on the area rather than the enclosure itself. So again, at this stage, I'd like to pause the presentation just to pass it out again, just to ask you guys, which of these type of areas best fits the kind of area that you currently employ in your production line environment?
Thanks again, everybody, for taking part in the poll here. For the following description of your test area, it seems that areas without protection from direct current is the majority of the case, and definitely need to fix that.
So we've now established the kind of safe working environment you could look to employ in your kind of production line environment. Now let's talk about the individual elements in terms of operator training that you should be looking to offer. Before we get an operator out performing the testing, it's important that there's four main sections of things that they really should understand. And I'm going to break this down into two sections of two, really. Those that all operators should understand, and those that the kind of skilled or supervisory level people should really be understanding. So we're going to talk about how they should prepare for working, the kind of things they should be looking for, how the equipment functions, what usage they're going to do from the functions, do they understand exactly what they're doing during the tests, how to inspect things like test leads and fixtures on regular periods, and finally how to kind of verify the equipment on a regular basis just to make sure it's doing its job correctly. Now, in terms of operator training, we often get asked kind of what's the minimum period that we should be doing this training. Well, it should be considered to be repeated as and when necessary. So if there are instances or occurrences of bad practice, again, that should be refreshed. But as an absolute minimum, we'd probably recommend taking all of your operators through this process maybe once every 12 months. So firstly, let's talk about preparation for working. As an operator, they should be trained to understand kind of everything about the area itself. So when they enter the area, what PPE should be worn during that. So if there are any requirements from a health and safety point of view, and that could be external to the electrical safety testing, so things like high visibility jackets, but looking more into the safety testing, if they are required to wear high voltage gauntlets or maybe goggles to protect their eyes during the testing, that's the first step. The operator should understand exactly what's required of them when they get ready for working. They should be trained to operate any of the emergency stop features in the event that an incident was to occur. So do they understand exactly how the emergency stop features work, whether that is things like interlocks on the test equipment or indeed the emergency stop buttons. Again, they should be well trained to understand exactly where they're located and how to get to those in an emergency. They should also be trained to understand exactly the function of the role they're employed to do, and ultimately who shouldn't be able to enter that test area. So they should be trained to instruct those that they know have had no training to leave the area when it's live, or unless they are accompanied by a supervisor. So if somebody of a supervisory level is taking someone in there, again, that could be for training, that would be fine. But certainly whenever they're doing any kind of testing, they should ensure that only trained personnel who fully understand the risks are in that kind of area when it's live. Finally, they should always be taught to understand exactly where to find and interpret the instructions for use. So when you are creating your safe working environment, it's important that you create a document to allow them to understand exactly what happens inside the area. So any instructions for use within that area should be available to the operators. That could be as a physical document, literally left with the test area, or somewhere easily found within a kind of network environment. Once they're fully trained on understanding exactly what they need to do prior to the testing, they should then understand exactly the test equipment functions and the tests that they're going to be performed. So first and foremost, they should fully understand exactly what test you're being asked to perform. So not only understanding exactly what the test is, how it works, but what the risks involved are, where there is a potential hazard during that test period. They should also be trained to understand exactly how the test instrument is used, how to perform it safely, using the instrument, using the features within the instrument, and therefore understanding exactly what feedback the tester is giving the operator. So, for example, within the Seaward range of high-pot testers, we have different indicators for things such as pass or fail. We try to feed back exactly what the failure condition was, should a failure condition be met. But we also have kind of other warning signs, so things such as red lights when there is high voltage present, that actually illuminates on the tester, separate from the beacon. So all of those things that the tester does and the way it displays results and any kind of operator information should be fully understood prior to being able to go out and perform the testing. They should obviously understand that during the testing, in no way, shape or form should they be in contact with the product, unless of course we're using probes. And therefore, if they are using probes and having to make physical contacts manually, they should fully understand exactly how those probes are used. So if the probe has retractable tips, for example, they need to be trained to understand that when they make contact with the product, the tip shouldn't be exposed, the product contact should be made, and then the tip placed into position until the contact is met. But there's no exposed kind of metal work. So if you are using probes, again, make sure the operators fully understand exactly the functions of the probe, exactly where it needs to be to make a good measurement, but ultimately how to use it to perform a safe measurement. Now, getting on to more kind of skilled tasks that an operator should be asked to do. Again, at regular periods, they should be trained to inspect the leads and fixtures. And by doing that, we're looking for any kind of signs of wear and tear within the testing circuit that could either impair the measurement or ultimately that could lead to an unsafe test connection. So things like the connections, are they properly terminated? There's no loose strands, the cables aren't over time being stressed and maybe being pulled apart, and therefore we're starting to see the inner conductors. Any kind of signs of damage due to misuse. So if the probe's being dropped on the floor, is it starting to crack or show signs of stress? Or any fixtures that you use. So if you do make any kind of test jigs that have physical connections to the testing equipment, again, any signs of damage or misuse, any exposed conductors that could pose a safety hazard, the operator should be trained to spot those and ultimately then make that decision to take them out of service or make contact with a relevant person, maybe a maintenance or production engineer, who could come and correct the issue before further testing goes under place. Finally, let's talk quickly about verification of test equipment in terms of operator training. So again, this may be at supervisory level or a skilled operator should be able to perform regular verification of the test equipment. Now, ultimately by this, we're not talking about a calibration check. This is just a check that the equipment is picking up failures and alerting the operators to the fact that a failure condition has met. So in order to do this, we could use very simply just some known resistors, and they're designed to create a fail condition. So as a good example, I spoke earlier about lighting. We have a 5 milliamp pass fail limit, and we apply 1500 volts to that test. So we apply 1500 volts. We have a resistor that at 1500 volts develops more than 5 milliamps of test current, and therefore what we would expect to see is the tester pick up on that, fail the test, and stop the test safely. So on a regular basis, it's definitely recommended that a skilled operator is able to perform these kind of verification checks. Now, to make things nice and simple for you all, Seaward have a range of fault simulators designed exactly for this task. So if you do want to kind of pick this up and move it on a production line, we have a solution. We can very quickly kind of offer that kind of simple verification check. It should take no longer than testing the very first product. So it should only really add a couple of seconds onto your day from a production point of view. So that brings me to the end of operator training. We're just going to have a quick chat about the kind of things that you can look for within your test equipment, or when you're considering purchasing new test equipment, that can aid you in that kind of creation of a safe working area. So the first thing we're going to talk about are what we call fast react trip circuits. So a fast react trip circuit essentially stops the test the instant the fail condition's met. What we don't necessarily want to continue to do is we hit a condition where the fail point is hit. So let's say our tester has delivered more than 5 milliamps on our pass limit. And what happens is the test continues on until the end of time of the test, and then reports back that there is a failure. What we want to happen is, as soon as that condition is met, the tester will stop the test instantly and alert the operator that the fail condition is met. So we're looking for fast react trip circuits. We can also look for isolated test outputs. So the isolated test outputs are floating with respect to Earth, so effectively removing that ground path, which means that if the operator was to come into contact with one of the test outputs, there is no path to ground through the instrument, so therefore they're kept nice and safe. We alluded to interlocks a little bit earlier when we were talking about the enclosure scenario. Most testers nowadays on the market will have an interlock feature, or a guard switch as we call it within Seaward, and they're designed to instantly disconnect the output if the two contacts of the switch are placed into open circuit. So effectively a guard switch is very, very simply two contacts that need to be shorted together in order for testing to go underway. I would always recommend looking for a hardware-driven solution for this rather than something in software where you can switch it on and off, because we do then potentially look for a fault condition where the software fails and doesn't open the interlock. So the Seaward products are always developed with a hardware solution in mind. So it is a very, very simple hardware short circuit. If that doesn't exist, testing isn't allowed to go underway. So this can be linked to many ways. We spoke about the enclosure. We could link it to the doorway of the enclosure. If someone opens the lid during testing, the test is immediately stopped and the test voltage disconnected. Or if the lid is left open during the start condition of a test, then the tester will not allow the test to take place. It can also be used in many ways to create your area without automatic protection and to keep the kind of untrained out. So in many instances, people will use this guard switch to link it to the doorway, to the area, for example. So if someone wants to walk into the area, instantly that test voltage is disconnected and the area is safe to go into use. Automatic discharge of stored voltage. Now, whilst this isn't true for necessarily AC products, when you are doing a test on a DC component or using DC to perform a test, one of the features that, or one of the byproducts of that could be that we store energy within the product under test. And one of the risks then is we make the test, we store the product up with energy, we disconnect all the test connections, the operator comes and picks up the product to move it along in the production line, maybe for packing, and what happens is the unit discharges all that energy instantly through the operator. So nowadays, again, the Seaward range of testers are how products that Brad will talk to you about briefly in a moment. They all have a disconnect path. So as soon as the test is finished, the HAL unit or our test unit switch over to a discharge resistor that removes any stored charge. So by the time the operator comes to pick it up, the unit should be safe for contact. And then finally, we spoke about safety probes a little bit earlier on, making sure that they've got things like retractable tips. Again, make sure the probes you are going to use are specifically designed for that purpose. So have they got things such as the retractable tips? Are there items such as hand guards? So if they are physically using a probe, is there a barrier between the end of the probe, the hot end where the product's going to make contact, and the hand? So do you have a nice firm hand guard that would potentially stop the hand from slipping down and coming into contact with the probe? So that about brings me to the end of the presentation. So thank you for your attention. Just for further reference, if you do want any kind of further reading, I've just placed up on here the kind of standards that you could be looking to, or legislative documents, along with a link off to the websites to gain further information. We will be sending out copies of this presentation along with our guide to creating safe working environments. But what I'd like to do now is hand you over to Brad, who'll give you a brief introduction to some of our products, and then we'll open the floor for any questions you may have. So thanks again for your attention, and we look forward to seeing you again soon.
Thanks again for staying on for the presentation. We'd like to briefly introduce you to our industry-leading range of production line safety testers, the HAL series. Designed to increase productivity during tests, the HAL is a highly flexible tool for electrical manufacturers. Each HAL is capable of storing up to 6,000 test records and has the ability to download the results to a PC. Combined with a barcode scanner, full traceability of your product testing can be kept, giving you peace of mind. The HAL series is fully programmable. Test sequences can be created and stored, ensuring that the products are tested correctly time after time. For those wanting an automated system, the HAL can be fully remote controlled and integrated into any system. As you can see on the table, all of our testers in the HAL series will perform AC high pot at 50 or 60 hertz, a DC high pot, and an insulation resistance. For those that need tests that are earth or ground bond for their equipment, the HAL 103 adds that feature. In addition to traditional safety testing, our HAL 104 and HAL LED also adds the ability to perform load and leakage testing, ideal for those who also want to ensure the product is fully operational prior to shipping, potentially saving on expensive out-of-the-box replacement costs. The HAL LED is perfect for manufacturers of low power products who want the flexibility to perform operational checks, and is ideal for the LED lighting industry. Now that's the end of our presentation. Thanks again for your participation. If you have any further questions, please use the question tab on the toolbar and we will respond to them before we go. If you want to contact us after the webinar, the regional contact details are on this page.
Okay, well, just a thanks from me for everyone's attention today. As Brad said, if you do have any questions, please feel free to send them through. We will be looking at adding more of these presentations for production line environments, including kind of going into what the tests will be, how to perform them safely, and ultimately kind of what they require from you guys. But again, we'd like to open it up. If you do have questions, please send them through. If not, we'll hopefully see you on another one. Okay, well, there doesn't seem to be any further questions coming in. So again, thank you for your attention today, and I'll officially bid you goodbye.